Just 1 second. I'm just maybe you can't see, but now how will this go? So what do I do? Why is this not going? Okay. Sorry for this delay. Uh, so what we're going to discuss in class 27 is the Boltzmann Transport Equation considering collisions. So in the previous version of the Boltzmann Transport Equation, what we considered is at any point in time, if there is a way, if the distribution function is away from its equilibrium value, it was assumed that due to internal collisions, there's a relaxation time tau zero, and left to itself, the distribution function will relax to its equilibrium value within time tau zero. So that was the single exponential relaxation time approximation, where what is happening inside, what collisions are happening, that was not taken into account. But suppose you want to look at the in more detail upon the collision process, and you want to have correlations where two particles come in and then collide and go and occupy and change the distribution function, because if they collide, then the the velocity of the particles is going to change, thereby the distribution function themselves are going to change, and if there are multiple collisions, and the distribution function is going to change, uh, and if those details are going to be taken into account, then you have a more detailed expression for the for the collision. I mean, the collision process, the term which determines the collision process and thereby changes F, the so-called DC F, and that will be taken into account. Of course, the details of the scattering cross section, how two particles interact, how the interchange momentum. So two particles come in with velocity v1 and v2, and then interchange energy and momentum and go away in different directions. The details of that will, of course, depend upon the details of interaction. If it's an electrostatic interaction, or if it is a hard sphere interaction, or it's a short range interaction. So that will decide it. So the explicit expression for the scattering cross section will be left ambiguous in our discussion. But what we are going to discuss is, suppose you know the scattering cross section, then what is the general expression of and the scattering cross section will depend and change from problem to problem, because the interactions are going to change. But having known that, having known some other basic quantum mechanics or collision process or whatever, if you know the scattering cross section, then you can describe how the distribution function is going to change as a function of time, and of course distribution function at different points in space, and for different values of velocity, how are they going to change in time? So that's the point. So to do that, what we need is first a discussion of the collision process. We're going to rewrite. So if two particles are coming in and with velocity v1 and v2, where the observer is at rest, one can do the calculation, but it will help if we change the frame of reference, so that the observer moves with the center of mass of the two colliding particles, and that will help the analysis. So that's why what we're going to start with is a detailed discussion of how to change various coordinates, and having done that, discuss something called a inverse collision, and finally in the uh, last moments of the lecture, we are going to reach, we are going to start discussing the Boltzmann transport equation. So we'll start with the discussion of the collision process. So basically, this is from chapter 14 of Rife. So we are going to basically consider classical collisions, but scattering cross section you can also calculate quantum mechanically, right? So we're going to assume that internal degrees of freedom, like rotation, vibration, are unaffected by the collision, so that all that we are considering is two particles coming, exchanging momenta and energy and going away. Internal states are not going to change, so they are frozen. They have much higher energy. That's what we assume. And interaction depends upon the relative positions and velocities, of course, because if it's a long range, then two particles, even at high distances, relatively large distances, are going to interact. On the other hand, if they're short range, interaction to particles is going to come in straight lines, and only when they are interacting at their momenta and velocity going to change. Um, so as I already said in the introduction, we are going to consider a more detailed analysis of the collision process and thereby relaxation to equilibrium. We are not going to solve any problems. We are just going to state the Boltzmann transport equation, and in the future, that is going to be the starting point of many other discussions and calculations and so on. If you are in statistical physics or plasma physics or astrophysics or whatever, so if there are particles colliding and the distribution of velocities are going to change at different points in space and time, then you're going to start using the Boltzmann transport equation, whatever be the microscopic interaction. And yes, so it will be left. We are not to solve. We are not going to solve any problem. We will just write down the transport equation. With that background, let's start discussing that there are suppose two particles with velocity v1 and v2. So this is this curly v1 and v2, which are approaching each other. The different point at different points in time, their position is r1 and r2, which are of course changing as a function of time. And here there is a collision, and after collision they go out with velocity v1 dash and v2 dash. We are considering that the gas is dilute. There are only two particle collisions at a time, no 3, 4, 5 particle collision, no interchange between particle energy and momenta in a 4 particle collision. So that's a simplification for valid for dilute gases, right? So v1 and v2 are the input velocities, and they go out with v1 dash and v2 dash. We can always write the total momenta of the incoming particles as m1 v1 plus m2 v2. That's the total momentum. And during the collision, since so there's just two particles, there's no third, fourth particle, or they're at least not interacting with each other, the total momentum will be conserved during the collision. So the relative velocity can be written down as v1 minus v2, and in that case, the center of mass velocity c is m1 v1 plus m2 v2 plus m1 plus v2, right? Which is the total momenta divided by momentum of the two particles, because m1 v1 plus m2 v2 is the center of mass velocity, and divided by m1 plus m2 is the velocity, is the center of mass, right? And since momenta remains unchanged during the collision, the center of mass velocity remains unchanged before and after the collision. It's a consequence of momentum conservation, of course, right? Now, the position of the center of mass, which keeps changing, of course, because it's finite velocity, can be written in terms of m1 r1 plus m2 r2 on m1 plus m2. Right? And this r1 is a function of time, r2 is a function of time, because these particles are moving as a function of time. They are moving towards each other before they collide. So the uh, center of mass position, of course, changes, and it moves with velocity c, of course, right? Moreover, the relative position can be written in terms of r1 minus r2. So if it's r1 minus r2, then this vector should have actually pointed in this direction, because yeah, so it should have pointed in this direction. Or if the vector is this, then we should have written, no, this is in the right direction actually. It's going from r2 towards r1. Yeah, this is right. R equal to r1 minus r2 means the vector shall point from r2 towards r1. Correct. So the direction of this vector is correct actually. And one can define the so-called reduced mass, which you must have seen in classical mechanics, as m1 m2 upon m1 plus m2. So why did we define such so many quantities? The reason is you'll see soon. Uh, we are going to write the velocity, calculate the velocities in a frame where the observer is moving with the center of mass of the two particles. The kinetic energy in general can be written as half m1 v1 squared plus half m2 v2 squared, and this in turn can be written as 1 upon m1 plus m2 c square, this is the center of mass velocity square, plus half mu v square, right? This is the relative velocity. So just to remind you, this was the relative velocity. So the individual velocities were written in with these curly v, yeah? And this capital V is the relative velocity. So you can just substitute the terms, the expression for c squared and v squared, and you will get half m1 v1 squared. You will get this. So now what we are going to do is change of coordinates. So what we have done is written down the kinetic energy in terms of the center of mass velocity and the relative velocity. Now, since c square remains unchanged before and after the collision, and you know that, I mean, we are considering only kinetic energy, or rather the potential energy of interaction is relatively small. So all the velocity is, I mean, all the energy is essentially kinetic energy. There's an assumption going here. We are assuming weak interaction. The expression for the potential energy is neglected. Right? And this is considered very high velocity compared to PE. That's why, because in general, energy is conserved, right? But we are writing the kinetic energy is conserved. It's only possible if you consider weak interaction, the potential energy contribution to the energy is neglected, right? Yeah, or even if they are interacting where the kinetic energy has changed, once they go out, they're out of the range of the interaction, right? Then the total energy, even if there was strong interaction, two particles had come in, they had interacted, and they are going out, and they have stopped interacting with each other. So all the potential energy has been converted to kinetic energy. So we are looking far away from the collision. So then all the energy is again kinetic energy. So, okay, you don't need the approximation of weak interaction actually, right? So in that case, the kinetic energy remains unchanged after the collision. The center of mass velocity remains unchanged, which means that the relative velocity after the collision, or rather relative velocity square after the collision, is going to remain unchanged. So therefore, if the relative velocity of the two particles was v, and after the collision v vector, and the relative velocity after the collision is v dash vector, it says that the magnitude will remain unchanged, but the direction can be different. So v is not equal to, so vector v is not equal to vector v dash, but the magnitude remains unchanged, right? That's the idea. Now, yeah, so if you talk in terms of relative velocity, yes, the direction has changed. If you're moving along with the center of mass, two particles are coming with a relative velocity uh, v v. They're moving away with relative velocity v dash vector, but the magnitude remains the same. That's the message. Now, what we are going to do is write the momenta of each particle in the coordinate system where the observer is at rest in terms of c and v. You're basically doing a variable. So P1 is equal to M1C1, sorry, M1C plus mu V. And one can easily see that because if you substitute C M1V1 plus M2V2 equal to M1 plus M2, and mu is M1 M2 upon M1 plus M2, and this is the relative velocity, right? Then you can just expand this and you can show that this is equal to M1V1. So this is a valid term, and similarly you can show that P2 can be written as MC2 minus mu V, right? So now writing the positions of particles 1 and 2 in terms of the center of mass coordinates. So RC is the position, instantaneous position of the center of mass, right? And so if you calculate the position of a particle with respect to the center of mass itself is moving with velocity c, then you can write R1 star, which is R1 minus RC relative to the center of mass velocity as R1 minus this is the center of mass coordinate. And after doing a bit of algebra, so you just take this side. So what you get is this R1 star can be written as mu by M1 R vector, right? So with respect, if you're sitting on the center of mass, you can see that the first particle is at a certain distance mu by R vector, which is the relative position. So it's going to be mu by R vector, where R vector is the relative position. And similarly, R2 star, you can see, can be written as mu by M2, this R vector. So if you are sitting on the center of mass, you're going to see that one particle, so the position of one of the particles is R in the direction R vector away in magnitude mu by M1, and the other particle is at a position opposite to that minus R, that is mu by M2 into R. So they are coming straight at each other. If you are sitting at the, they're coming approaching the center of mass, right? And that's obvious because during the collision they will be right next to each other to the center of mass. So they're approaching each other with these two vectors, which are the magnitudes are the different, but direction is exactly opposite that of each other. So that's the message here. So with respect to the center of mass, which is moving, you would say, so if you want to write V1 dash, it can similarly be written as center of mass velocity mu by M1 mu by M1 V dash, where this is the vector which is like going the relative velocity between the two particles after the collision, and the velocity of the second particle can be written as c minus mu by m2, again v dash but with a minus sign, which means two particles are approaching each other with velocity. Well, the velocity is not equal exactly. Uh, the So where did the expression for relative? Okay, they are approaching with respect to, so the yeah, so the direction is opposite, but the magnitude is different because this is mu by m1 and this is mu by m2. And similarly, when they're approaching, this should be v1 vector, this should be v2 vector. The velocity, yeah, sitting on the center of mass, it is moving. So with respect to the center of mass velocity, one is approaching the center of mass with velocity mu by m1 into v. The other has approach velocity mu by m2 because it's a different value v but opposite direction, and then thereafter they go apart in two different directions, right? They go away with two different directions, but the magnitude of v and v dash uh, is going to be the same. This is the relative velocity. This is the magnitude is going to be the same, but of course the directions, the vector quantity are not the same. So with this, what we want to calculate is the scattering cross section. So if v1 and v2 collide and go into v1 dash into v2 dash, and it has, and these two, I mean, two particles are colliding, but depending upon the impact parameter, how far they are or how the distance of closest approach, what velocity they can. So, so depending upon the distance of closer approach, the value of v1 dash and v2 dash would be different. It will depend upon the details of the interaction. So what you're going to say that if two particles are coming with velocity v2 and v3, what are the all possible values of vectors that they can take? So that will lead to a decrease in f v1 and f v2. If you integrate over, I mean, because they're going into different v1 dash and v2 dash. So they're basically going. So this quantity is essentially the unit flux per unit time of particle 1 incident on particle 2 with relative velocity v, right? Uh, and after scattering emerging with the with the respective final velocity v1 dash and v2 dash, that is, they have with respect to the center of mass, uh, they have velocities, well, with respect to the, so the relative velocities are mm, they're not identical because, yeah, with relative velocities mu by m1 into v dash and mu by m2 into v dash, right? So even with the center of mass velocity, they have different magnitudes. So this is one has to be careful about that. Now, going into these different v dash and minus v dash, right? So, are they going? this v dash magnitude relative velocity, but each particle is moving even with the respect to center of mass with different velocities, but the relative velocity magnitude remains same. The direction is not the same. Yes, they're emerging with v1 dash and v2 dash. Which is these terms, correct. Uh, and this v1 dash and v2 dash can be written in terms with, I mean, this is how you can write them in terms of c and v dash. But what we are going to say is this v1 and v2, this approach in two different directions, that is equivalent to mentioning the values of theta and phi that they scatter into, because the magnitude anyway remains the same. All that you have to calculate is the direction, and hence one can, it's relevant to equally mention is in terms of theta and phi, right? Because the vectors v dash and minus v dash, the magnitude remains different for the two different particles, but they are uh, equal and opposite in direction. So you can just mention theta and phi, and that will specify, right? So equivalently, we can write about scattering cross section into an angle omega, solid angle omega, if you specify theta and phi. So this quantity d v dash d omega is the flux per unit time, where one particle is incident on the other with relative velocity v, and after scattering emerge in direction v dash in the solid angle range d omega dash about theta and phi dash. Okay, so I want to split this lecture into two parts. So this is where we stop, and then we start from the next. Yeah.